Hello, my name is James Halderson, and this is a video I've been wanting to do for a while. I got a little bit of positive feedback on some of the other videos I've done in the past. Just a heads up, I am still um, recovering from dental surgery, so I'm missing a bunch of teeth. So if I can't say certain words or whatever, I apologize. So this video, basically we're going to be asking the question, is the universe a gigantic quantum computer? And another question we're going to be asking philosophically and ontologically is there a computational basis for consciousness? And throughout this video, it's going to start off kind of soft and easy to digest. We're just going to be talking about philosophy, ontology, Max Planck's concepts, and some metaphysical properties of what Max Planck believed, one of the godfathers and the Nobel Prize winner in quantum theory. We'll go from there into some more esoteric and looking at some mystical concepts, some mysticism from the past, where people contemplated we'll specifically be looking at Greek interpretations and some Judaic mysticism of what consciousness was and the idea of God just generally what the idea of God was. And then we will be moving from there more into the actual premise of quantum computing, quantum annealing systems, what a qubit is, and walking through all of those kind of recent discoveries and findings over the last 20 to 30 years before we get into the final part of the video, which is a theory that I have been working on. I have been using AI to assist me in working through some of these more complex equations in theoretical quantum physics, to look at a basis for a physical basis in physics and mathematically for the universe actually being a quantum computer, and why that entails that consciousness might actually be this emergent mechanic from quantum computation, the quantum computation of the universe itself, and what implications this has, at least from my perspective. So we're going to be going through a whole bunch of different realms, from the more philosophical and metaphysical into the physical and the mathematical, just to talk about all these different paths, pointing to what I believe personally is a rationale for the emergence of consciousness and the nature of consciousness throughout the universe. So firstly, we'll just briefly look at our first slide here after my little introduction there. And we have Max Planck, who famously argued that consciousness is fundamental and matter is secondary and derivative of consciousness. He specifically said, I regard consciousness as fundamental. I regard matter as a derivative from consciousness. We cannot get behind consciousness. Everything that we talk about, everything that we regard as existing, postulates consciousness. The core philosophical stance was, he believed, and often referred to as a form of metaphysical idealism. He posited that the universe is essentially mind-like rather than machine-like. His most significant assertions include consciousness as the foundation. He stated, I regard consciousness as fundamental. I regard matter as derivative from consciousness. The matrix of matter. In his 1944 speech, The Nature of Matter, he argued that all matter exists only by virtue of a force, and behind this force we must assume that the existence of a conscious, intelligent mind, which he called the matrix of all matter. The inability to bypass consciousness. Planck believed that because our selves are part of the mystery we are trying to solve, we cannot get behind consciousness, though through purely scientific inquiry. So that was his belief systems. We should pause it here before we move forward, that Max Planck was very religious, and he was a fundamental Christian, and I believe that he grew up Catholic. So a lot of his belief system probably edged on Christian theology, which derives from Judaic mysticism and theology beforehand, and hence Max Planck's concept was that consciousness was the all. It's the thing that existed first before any physical matter or energy, before the Big Bang and the hot dense state and everything that we talk about inside of theoretical physics. But Max Planck believed that there was consciousness there before, and that consciousness would imply God, the Christian theological God. Of course, myself, not necessarily being Christian or religious, uh, I kind of take a lot of issue with that. And the whole reason why I started going down this path was because we'll look at the double slit experiment here and what that is. So, if you're not very familiar with physics, the double slit experiment was an experiment that they sent a bunch of light and they had two slits, and then they see an interference pattern, which we can see here if you can see my mouse. And this interference pattern showed that, oh, well, there's waves here, right? Because when we look at wave function equations, we know that they can positively or negatively interfere, and then that would leave behind some kind of interference pattern. So, of course, when we seen that there was interference patterns, we assumed, yes, it's gotta be, light's gotta be a waveform. Now, the interesting thing is that the double slit experiment also brings into the equation the observer effect. So what happened was we watched it happen, and all of a sudden it switched to there being finite particles or photons, and the interference pattern was no longer an interference pattern that would suggest that there's a waveform there. Instead, now the interference pattern was particles hitting this material they were using, and they could see that there's some imprint from the particle. And so the observer effect then assumed that when we were observing something, that would change the physical state of energy and how it interacted with matter. And when we turned away, it would return back to its wave-like form and back into this energetic state. Of course, this is so very bizarre because it assumes that observation changes the outcome of a physical experiment. Now, observation in physics, I should say as a caveat here before we get into the deeper stuff, that observation could be some kind of mechanical or technological interaction with this energy and matter. That also counts as observation. Observation does not necessarily posit a conscious observer. Now, the philosophical and the ontological perspective is that if matter and energy exists, and we can see both states dependent on observation, that there had to have been an initial point, right, where everything emanated from, the Big Bang, we can say, or some kind of energetic event in the far distant past, billions of years ago. Something had to have happened, and then what was that thing that happened? Because everything then interpreted everything beside it and interacted with everything in order to determine its state, right? Like all the states that existed, quark states and all these, anti-quarks and things, matter, antimatter, all of this stuff, like what Dirac talked about. This all had to have come from some event, and then that event had to be observed, essentially, for things to take a particular state. So, the philosophical debate that comes from there is it like what Max Planck was saying, in which he believed that it was the God above that observed in his consciousness, its consciousness, whatever that God above is, was observing everything into existence for it to be able to take an initial state? Or the other side of it, what I'm positing here, and the reason why I did all this research and came up with my own equations and just this whole thing on my own personal journey into theoretical physics and spirituality and just my want to understand the universe more could be there's intelligence observing things from the bottom up, and that it's not necessarily a god, but it's actually the matrix, the fabric of the universe itself, which is observing everything else, and everything is all, you know, witnessing its way into existence. And when I thought about this really deeply, I thought about like quarks and uh, qubits, and as we're going through quantum computing, we'll get into that debate later about what that entails, quantum computing and the nature of consciousness. But I really thought about how does this, uh, how do these revelations show that things at this smaller scale could actually be computational, and maybe consciousness emerges from these computational states. So that's my introduction here, looking at the philosophical, the ontological, Max Planck's ideas, which I am very inspired by Max Planck to do all of this work. We're going to move on to the second slide now, and we're going to start getting to some interesting metaphysical and other philosophical and how that ideas and how those actually mesh with reality. And so here we're going to be talking about the tetractys, and actually on the side we have the baryonic model of emanation. Not just emanation, but how these baryons are actually produced by different configurations of quark states. So we're just going to read on the side here before I go into my own interpretations, but in both ancient philosophy and modern particle physics, the tetractys describes a triangular arrangement of 10 elements that aligns or signifies the fundamental order of the universe. The Pythagorean tetractys, in Pythagoreanism, the tetractys is a sacred symbol consisting of 10 points arranged in an equilateral triangle with 4 rows. It represented the source and root of eternal nature, and was used by the Pythagoreans and the Mathematicoi, but that's a different discussion, to swear their most solemn oaths. The 4 rows of the tetractys symbolize the progression of reality. On the first point, we had the monad, which represented unity and the divine source of everything. On row 2, the second point, we had the dyad, representing duality in the first dimension, which was a line. On the row 3, we had the triad, representing harmony in the second dimension, which was a plane. And then on the fourth row, the tetrad, representing 4 classical elements, earth, air, fire, and water, and the 3-dimensional world. Of course, if you're into magic, and all of these other concepts, alchemy and stuff from the classical era, you will know that there was the 4 primary elements, earth, air, fire, and water, and they believed that everything that in existence was some combination of those. And we will get into why that is interesting in a bit here when it comes to quark states. But the baryon tetractys, or the decuplet, in modern particle physics, the baryon decuplet, the group of 10 spin 3/2 baryons, is often visualized as a tetractys. This arrangement arises from the SU3 flavor symmetry, which organizes particles based on their quark components, up, down, and the strange component, or strange quarks. The 10 particles are arranged by their properties of isospin, the horizontal axis, and strangeness, which is the vertical axis. On the top row, we have the delta quartet, which has these delta 2 plus, delta 0, and delta negative, consisting of up and down quarks. Second row, we have the sigma triplet, which is sigma plus, sigma 0, sigma negative, each containing 1 strange quark. The third row, we have the Z doublet, each containing 2 strange quarks. In the bottom row, we have the omega minus singlet, containing 3 strange quarks. So, the tetractys here, we can also see at the bottom, is very similar to the tetragrammaton. The tetragrammaton, sorry, it's a hard word to say right now because of my condition. the tetragrammaton was this idea. It's basically the name of God, the name of Yahweh, or whatever it was that apparently emanated into existence. The tetractys we had, um, like we talked about in Pythagoreanism, was this shape that represented the four different um, emanations of existence. And then, of course, we have the baryonic model here, the decuplet, which shows how quarks can be arranged into all these different theoretical particles. And basically, what that is, it's basically like the table, the periodic table, sorry, of quark states. And everything that we know of, at least when it comes to baryons, all the baryons are comprised of these quark states. And of course, there is other particles that are non-interactive with the strong nuclear force, um, like electrons, let's say, that aren't comprised of quarks. They're their own hadronic system. But the what we consider giving mass, uh, protons, neutrons, everything within the core of the atom, other than the electron orbits, is comprised at a subatomic level of these quark states. And the reason why this is all interesting, the tetragrammaton, the tetractys, and everything we're looking at here, is because if we move to the next thing, in Kabbalah and in Judaic mysticism, basically there was a fundamental blueprint of existence representing the totality of everything, the source of all reality. It consisted of the Hebrew letters Yud, He, Vav, and A, which symbolize the past, present, and future. Now, this is very interesting because the four worlds, the world one, emanation, world two of creation, world three of formation, the world four of action, basically the tetragrammaton and the Kabbalah emanates out into these four distinct stages of emanation, let's say. And that's very interesting to me because if we come back one slide and we look at the baryonic model and the decuplet, that it's basically the same thing, right? It's the same thing as the tetractys, which these are metaphysical and philosophical ideas. But then when we look at nature and quarks and what's at the core of baryons, we see that they also follow a similar pattern of emanation and increasing complexity, which goes to show that this concept of, like, they were onto something, basically, is what I'm trying to say. That their minds, philosophically, at the time, without the machines and everything that we have today, were catching on to some kind of nature of the universe and of consciousness and existence, reality, that was passed down for thousands of years through, you know, their mystic rites and, you know, the high priests and the Greco-Roman mystery religions, whatever you want to talk about there. But there's something there, and it's very fascinating to me that they were contemplating these ideas so far back, and that now that we have the machines and we have the instruments to go out there and test for things, we can kind of prove that some of these observations have a grounding in reality. So I just wanted to bring that up before we get into the really complex stuff, because it's going to go very complicated from here. If this is complicated already, it's going to get 10 times more complex as we look into the nature of reality. So, on to our next slide. So, we're just going to be looking for the next few slides at how quantum computers work. Specifically, we're going to be looking at quantum annealing, which is how the D-wave computers work. We'll also be looking at QUBOs, which are quadratic unconstrained binary optimizations. And that's a big mouthful, we're just going to say QUBO from now on, to describe basically if I have a physical problem, I have some kind of thing that I want to solve, I have to take those branching paths of this could happen, that could happen, what is the most likely thing to happen, like in a statistical model. And I'm going to break that down into a QUBO, which is then basically the instructions that I feed into a quantum computer. Currently, quantum computers do not have any programming language. There's no C or assembler or binary. It's kind of akin to the binary code of a quantum computer, especially when we're talking about the D wave. So we're just going to go into a little bit of stuff here before we move on. We have quantum annealing as a specialized quantum computing paradigm designed primarily to solve complex combinatorial optimization problems. Unlike gate-based quantum computers that use discrete logic gates, quantum annealers rely on the continuous evolution of quantum system to find the lowest energy configuration of a problem, which corresponds to the optimal solution. So we're going to be looking at energy landscapes. Problems are mapped onto an energy landscape where the valleys represent potential solutions. We're also going to be looking at superposition, which is the process that begins with all qubits in uniform superposition, allowing the system to explore many potential solutions simultaneously. Quantum tunneling, this allows the system to pass through high energy hills, local minima, that would trap classical algorithms, increasing the probability of finding a global minimum. In adiabatic, sorry, that's a weird word, evolution. If the system is evolved slowly enough through annealing schedule, the adiabatic theorem guarantees it will remain in its ground state, eventually settling into the optimal solution of the problem. And the key hardware that we're looking at is the D-Wave system, the primary commercial developer of quantum annealers. There are new systems like the D-Wave Advantage utilizing the Pegasus topology with over 5,000 qubits. Qubits and couplers, annealers use some superconducting loops of qubits controlled by magnetic biases and linked by couplers that define the relationships between variables. And hybrid solvers. Modern applications often use D-Wave's hybrid solvers, which partition problems between classical heuristics like simulated annealing and quantum hardware to handle larger real-world scales. So, basically, all that aside, I'm just going to be reading like I'm getting AI on Google to pump out me a basic summary or synopsis for what I'm looking at here, and then I'm going to go through how it works out of my own accord. So basically, you have this superposition state, and then it goes into a higher order curve, and this higher order curve, this process of going from lower order curve to higher order curve, is the annealing process. And then what happens is that there's troughs where the the state of the system can go into for each qubit. It can assume one of these troughs. Now the interesting thing about this system is that after all this work that we're doing, and we're going superconducting systems, and close to absolute zero, and there's all this work that has to be done to get it to start operating, and at the end of the day, at least with quantum annealers, we're actually going back to a essentially binary system, because each state, even though it does exist in a superposition, that position, the wave function collapses, and then we get a 1 or a 0, dependent on if it's the local minimum and the local maximum. So that's quantum annealing systems, and we need to know a little bit about quantum annealing systems, even though it talks about here gate-based quantum computers, and I will go into why that later, why gate-based is actually what I think is going on with quarks at a subatomic level. So we're just going to look at the Bloch sphere here and what the Bloch sphere represents. And again, I'm going to be trying to explain this. I'm not going to go into the specifics of the mathematics, but basically just what you have to understand about the concept from a conceptual level, what this stuff means. So, the key components of a Bloch sphere: the poles. The North Pole represents a 0 ground state, and the South Pole represents 1, the excited state. The equator points to the equator representing equal superpositions of 0 and 1 with different relative states. The plus and minus states lie on the x-axis equator. Bloch vector. A vector originating from the center of the sphere. If the vector tip is on the surface, radius equals 1, it is a pure state. If it's inside the sphere, radius is less than 1. It represents a mixed state caused by decoherence or noise. And then angles, we have the theta and the phi angle. These two parallel parameters define the qubit's position. The polar angle of the z-axis determining the probability measure of 0, 1, and the azimuthal angle in the xy plane representing the relative phase. Here's a mathematical representation of what we're looking at. Basically, what a Bloch sphere is there's 0 and there's 1, okay? And a qubit exists in a superposition between 0 and 1. So a binary bit, when we talk about classical computers, it's either on or off. If it's on, it's 1. If it's off, it's 0. And everything going on my screen right now, and everything, if you're watching this on your phone or if you're watching this on your computer, everything that's going on is basically just information encoded into the binary base 2 system. And it's just on and off, and there's billions and billions of switches going on, and they're just communicating this, capturing that data, passing it somewhere else. It's all just data at the end of the day with ons and offs. Now, what a Bloch sphere is basically is that it's actually the surface area of the sphere, and that surface area represents all these different potentialities, all these different states that exist between 0 and 1. So what 0 and 1 is on a classical computer, that's a Boolean operator. Now, the interesting thing is that if you look at all real numbers, not just Boolean integers, which is like, is it 0 or is it 1, right? There's no decimal point, there's no floating point there. But if we look at 0 and 1, how many numbers actually exist between 0 and 1? It's infinity. That might not be something that you know, but if I take 1.0, 1.1, 1.01, 1.001, 1.0001, and I keep doing that, and that can even be like 1.08, 1.03, whatever. I can have an infinite amount of decimal places, so I can have an infinite number of combinatoric combinations of numbers from 0 to 9 inside of those decimal places. Thusly, what's going on is that there's, in theory, an infinite number of states that exist, but that's only when it exists in superposition. So when you run the quantum computer machine, what's going on is that you're exciting everything and putting it all into an excited state, and it exists in superposition. Then you collapse all the waves at once, and then what that does is it assumes some local minimum or maximum, some kind of state out of that, and that collapsed state, within an instant, all those superpositions collapse, and we get, like Schrodinger's cat. Is the cat alive or dead? Let's say we have 1,000 boxes, and we check all the boxes in an instant. We know how many of the cats are dead, how many of the cats are alive, and that's good for modeling some kind of problem that has multiple different avenues. It can go this way, it can go that way. Like there's some good ones like the nurse scheduling problem they always use inside of this field of quantum mechanics. Another one is the classic delivery man problem that you may have if you've taken like statistics or if you've taken applied mathematics. You might know the delivery man problem. But all this complex mathematics, you don't really need to know it for this video. If you're interested in it, basically what's going on is that it's a wave function, basically, but we're just looking at the wave function is inside of a theoretical sphere, and when it collapses, the point lands somewhere on the sphere's surface area. That's basically all you need to know. That's what it's saying. On to the next thing. So the reason why I talked about all this stuff beforehand is because, again, before we go into anything, I just think it's interesting that we see these, triangles, and we see like what people would say is the Star of David, the hexagram with the six-pointed star, right? And that these kind of orientations appear all over the place when you get into particle physics and everything. And it might just be my bias for geometry, because I really like geometric correlations between things. It might just be my bias that sees this, but they're all over the place. Hexagons, hexagrams, triangles, pentagrams, pentagons. because these are the most optimal geometric configurations, and when we're talking about crystal lattices and a whole bunch of stuff that's off topic here, but um, we see in here with the tetractys, right? We can think about Sierpinski triangles or Pascal's triangle and how mathematically that's very similar to what's going on here. Um, we looked over here, we looked at this is quarks and antiquarks and how they annihilate each other inside of a little diagram here, and we can see that that also formulates uh, one of these hexagrams. A hexagram happens here when we're looking at how the Kabbalah operated, right? And we're talking about moving through the emanations and everything. A hexagram existed within the Kabbalah, so uh, it's interesting that these esoteric themes, these mysticism, they show up all the time when you're studying this stuff, and I don't think that's a coincidence. I don't think it's accidental that we see the same structures. Because, again, like I was saying before, and I'm kind of going on a tangent here, this stuff gets me really excited. I think the great philosophers, like we're thinking about Pythagoras, for instance, as a primary example, I think that when they were, thousands of years ago and they're studying this stuff, I think they were really onto something. They were getting some kind of transmission, the human mind being what I believe a collection of these computational states. It can be in tune with the greater computational universe, and it's like we're like little microchips and there's a big computer system and we're all aligned on the same network. That's the way I look at it. We're going to get more into that in a few slides, but for now I just wanted to kind of every time I look at this stuff, and I just feel really exhilarated by the fact that a lot of geometric um, these geometric correlations exist all throughout nature, all throughout uh, quantum mechanics, all throughout physics, all throughout chemistry. So, speaking of crystalline structures and how things work, we're going to talk about the qubit lattice algorithm is a quantum-inspired computational method used to simulate complex physical systems, such as Maxwell's equations, the Schrodinger equation, or fluid dynamics, by representing fields as a set of qubits distributed across a spatial lattice. So, we have a structure that consists of interleaved sequence of unitary collision and streaming operators. Collision operators act locally at each lattice site to entangle the qubits, mimicking quantum phenomenon like the formation of Bell states. Streaming operators move this entanglement to neighboring sites, effectively streaming the data through the lattice. Continuum limit. When these operations are repeated, they recover the dynamics of continuous physical equations like Maxwell's to second order accuracy in the lattice spacing. So basically, what this is trying to say here is that quantum computers, for instance, let's just say that we had like a 12 qubit system or an 8 qubit system, whatever it is. There's actually different kinds of qubits here. There's auxiliary qubits and there's a data qubit. And so the data qubits are entangled with each other, but they're also entangled with auxiliary qubits in between. And these auxiliary qubits are there almost as data correction, but also to keep the system stable. So it's a constraint system, and we're going to be looking more into why constraint systems are so important when I get into my theory and the mathematics I've been working on. But essentially what's going on is that these data qubits are used to compute the actual problem, and the auxiliary qubits are there to keep the form of the lattice and to keep everything stable and succinct. Um, yeah, so basically that's what's going on with all of this, is that you have two different kinds of qubits in a system actually, and that you need to entangle qubits to auxiliary qubits. Oh, sorry, I had a brain fart there. What I was going to say is that if you know anything about computation and like let's talk about like 8-bit systems, or when we have a byte, 1 byte, which is 8 bits, usually 7 of those bits will actually be used for holding some kind of information or holding something in memory. And then you'll have one bit, usually the first bit, that will be something called a parity bit. And what that parity bit is, it's there to help maintain the integrity of the following 7 bits. So it's kind of the same thing as a parity bit. It's like a parity qubit, these auxiliary qubits. They're there to help with the structure of the whole thing, but they're also there to kind of reverse engineer the information if something goes wrong. Which these systems, even though they're very complex, they do have relatively high failure rates, at least compared to a regular classical computer, because of all the, you gotta isolate the noise, you gotta have it at near absolute zero. There's all this stuff going on when we're trying to do our own quantum computers that it doesn't happen. Like, it's very rare that some outside inference is gonna mess up my computer chip on my laptop I'm recording on right now, whereas that's very likely inside of a quantum computer. Okay, next slide here, and I'm sorry my mouse is, I think, because I've been recording so long, my mouse is starting to just die down a little bit. So, we're going to be talking about the quantum perceptron, and then things are going to start getting interesting from here, because in quantum machine learning, QML, the quantum perceptron is the fundamental building block for the construction of quantum neural networks, QNNs. It adapts the classic perceptron, a linear classifier, into quantum regime by leveraging quantum gates, superposition, and entanglement to process information. Key models and mechanisms. Several theoretical models of quantum perceptrons have been proposed to overcome the linearity of quantum operations and mimic classical activation functions. There's the Grover-based perceptrons. These models use Grover's algorithm to search for misclassified data points during training, offering a quadratic speed-up over classical methods. Variational quantum perceptrons. These use parameterized quantum circuits where weights are adjusted by classical optimizers in hybrid quantum classical loop phase estimation models. One early approach uses the quantum phase estimation (QPE) algorithm to simulate the step activation function of a classical perceptron, and Hamiltonian dynamics, which is what we're going to be looking at soon. Newer models, as of 2025 to 2026, define the perceptron through an analog dynamics interacting qubits, allowing it to approximate any unitary operation and making it more expressive than classical neurons. Now, I'm sorry, this is some pretty heavy stuff that probably made no sense to you at all, because it makes it, a lot of the stuff in there is jargon that I myself am recently researching. But essentially what the perceptron is, the classical perceptron, what they're talking about, is that when we're making neural networks, and the very basic neural networks that existed before these complex machine learning systems, which themselves are based upon the concept of neural networks, there was something called the perceptron. And all the perceptron really does is that it's a sum, right? It takes, let's say I have n amount of inputs. I have a summer, which takes all of my inputs together. So if we look here, we have, it looks like this is phi. I can't really tell, but you have all these different inputs here, these different quantum inputs, right? My mouse is being weird, I'm sorry. And they're all pointing to this summer. And so the summer takes all of your inputs and it checks them, and like it finds what is the sum of all these different numbers or all these different inputs, and then it produces some kind of result based upon its pre-programmed biases. So basically what the perceptron is it's perceiving data and it's giving you some kind of response. That's the basic idea of it. It's kind of like the eyeball of the neural network landscape, that it brings in all this information and then it has to interpret it in some way. And then so a quantum perceptron is, we take the idea of the perceptron and this thing perceiving data, perceiving different inputs, and we're modeling it on quantum systems. And the reason why that is so important is because basically, now we're getting into the interesting stuff. So we're 39 minutes in and I'm finally going to talk about my theory for the universe and what quarks actually are. So, a quantum perceptron, I have these quantum states, like we talked about before in that quantum crystal lattice, right? The quantum machine learning algorithm array, and all those points, the bits, the qubits and the parity qubits, the auxiliary ones, that when some information, a QUBO, is fed into it, this is a QUBO equation here. When a QUBO is fed into that machine learning algorithm, all the states collapse, and then I have, oh, there's some dead cats, there's some alive cats, if we use Schrodinger's equation as an example. And then, so what happens is that after those states collapse, these are the collapsed states, they're fed into some kind of summer, something that sums everything up together, and then finds, oh, well, this must be the result of that collapse, right? Of all those wave function collapses in the system at once. I have to find some solution out of that information. And the reason why this is so important is because with quarks, my belief system is that each quark system, each baryon, and quark systems and everything interrelated to the baryonic model and how quarks operate, each quark is actually one of these perceptrons. And it's interacting with the quarks and the the energetic states beside it and the different forces, right? And after it interacts with those nuclear forces, with the electromagnetism, with everything, it creates a state, and then those states are summed together by like the atom is actually the sum of those baryonic states as a perceptron. So it's being perceived in some way. It's being perceived by the atom itself. It's the atom itself is perceiving not only what's happening within the atom at a subatomic level, but it's perceiving those states together are inside of unified systems, and those are perceiving each other. And when you have this happening billions and billions and trillions and quadrillions and however many atoms there could possibly be in the universe, which is some unknowable number, that is what the origin of consciousness is. It's all these systems interacting and perceiving each other together computationally in a similar way to how we're trying to mimic the perceptron with quantum machines. We're actually not mimicking anything. Well, that's wrong. We're mimicking what the universe does itself. It's technology imitating the universe over again. And we're just coming to this point now where our technology is becoming advanced enough for us to realize that the universe itself is, in essence, a form of technology. So here we are now, we're at the big moment. The next two slides are the system that I've been coming up with and using. I've been using ChatGPT and other AI models and everything to kind of help me come to get my ideas more into a mathematical framework. I tried working on the frameworks myself, and I just never came up with anything that worked. But then when I started using AI and everything, I realized that it made sense to the AI, my idea that a quark is a ternary computational system. When I was writing this down and coming up with my ideas for how a ternary quark could work and how ternary quantum computation could work, and then I fed some of this stuff into the machine learning algorithms, and they're like, yes, this is how it should work, this is how it could work. So basically what's going on here is that there's three major terms here inside of this Hamiltonian. The first major term is the local spin interaction, which is the S. So this is actually it's actually the sum of these singlets, which are quarks interacting with other quarks, just two quarks mix with each other, next to each other. Okay. Now this is interesting because matter itself is actually three quarks make a baryon, right? And there's something called the color pairing rules and the color theory here, quark color theory and quark chromodynamics, which we'll go into a little bit, but it's not real colors. It's just kind of the same idea that um, there's all these potential, there's like trillions of different potential combinations, but most of them don't work. So they came up with this coloring system in order to make a color wheel of sorts so that we could kind of hypothetically tell which quarks will work with which other quarks to create um, baryons that could actually exist in the universe. So the first one is the quark spin states, which is a quark has a spin, right? And the spin is either up or down spin. And that up or down spin is going to be equating to positive and negative charge, essentially, inside of this system. And so what the first local spin interaction equation does is it's actually like a constraint system. So it's in this Hamiltonian, it's a constraint in the Hamiltonian space to say um, this can work with that, like the color wheel concept that is already inside of theoretical physics. But it can't work with everything else, and it can only work with the ones that actually exist in nature, and that's because it's constraining it like to a certain lattice that is feasible and makes sense and is reasonable for quantum computation. Okay? So then we have the strong constraint, which is the middle one. And what this does is it forces the sum of the spins of each cluster to be zero or minimal. So what this means is that those clusters of quarks, right, just like we were talking briefly here about this color pairing rule, is that quarks must eliminate color, and antiquarks would so quarks would be white, antiquarks would be black, in these triplet pairings to be reasonable baryons to actually exist in nature. Um, this constraint model here, the second constraint, is to constrain um, how color confinement works within the system, and so that only things that have spins that equal out to zero and not out to some because zero is the colorless thing, and all the ones that we know about are colorless inside this quark color model. So it's constraining that so that only the ones that equal to zero, so only feasible quark interactions and only ones that will lead to a logical zero can be used within the system. And then the final one is that we have the kinetic state transition term here, which this is like more of a classical Hamiltonian if you're used to Hamiltonians. And this is just mathematically saying that this is the quantum dynamic part of it with superposition and tunneling. So when we were looking at the quantum annealing earlier here and how qubits inside the D-wave system are basically quantum annealed waveforms, and then we find this will read out to a matrix, and that matrix, it will be like a Dirac matrix where there will be positive states and negative states, which in Dirac's case means matter and antimatter, but we're only looking at the matter side of the equation because we only want to understand how these ternary quark units could be in some way computationally relevant within reality. And if you know anything about physics, matter and antimatter will annihilate each other, so we don't care about the antimatter side of the thing. All we care about is creating usable singlets to make ternary logic gates, and that this should explain the nature of quarks within the universe. And this is big stuff. It might sound like it probably sounds out of left field and doesn't really make that much sense, but that's basically what's going on here. So this is where I'm at with my theory. There's one more part to it here. So basically here we're going to look at the three different constraints, the three different terms within that Hamiltonian equation, and how these align to specific constraints or different types of logic gates. And then we'll be looking at how those equate to logic gates and systems that we're already using inside of computation. But most of these are ternary gates. And like I talked about before, I should talk about here quickly, binary is what we're using for the computers. It's a 1 or a 0, and that's base 2. Now, that's not just the only base, like everything that we do is in base 10. There's duodecimal systems, which is base 12. There was the sexagesimal system, which the Mesopotamian used, which is base 60. Blah, 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 blah. There's all, you can use any numerical value as a base for a system. And what a ternary system is it's actually using base 3. Why base 3? Because it's logically consistent with what we see in the universe. Again, we see powers of 3 happening over and over again. We see triangular systems, we see hexagrammic and hexagonal systems, which are powers of 3. So it makes sense that these crystal lattices and everything that's going on are defined by something that is at the power of 3. And a ternary computer is, instead of being 0 and a 1, it's a 0, a 1, or a 2. We have another state. That also makes a lot more sense when we're talking about quantum computation. Because as I explained before with the quantum annealing systems, if we just go back there, these D-wave systems here, we're doing all this extra work and then we're creating an annealed waveform, and the annealed waveform collapses and it's either a minimum or a maximum energy, and it's a 1 or a 0 again, so we're back to binary again. So we did all that extra work just to get back to binary. But with ternary, you could have a -1, a 0, or a 1, or a 0, a 1, or a 2. It makes sense inside of quantum mechanics for it to be negative charge, negative spin, down spin, up spin, or positive charge, or neutrality, right? And so we're just going to look at these 3 different kinds of terms here, and how those align with these ternary gates that are used. Not very often, but there is examples of ternary computers out there in the world today. The first one we're going to look at is the pairwise constraint gate, which we have this here. So this first term right here, which applies to the local energetic penalty that enforces compatibility and correlation between neighboring ternary quark states. So basically this is just a constraint, and it's just saying this spin and that spin, the sum of them together to the power of 2 must be equivalent with what is observed in nature. Okay? And this equates to a pairwise constraint gate, which we can see down here at the bottom. Pairwise constraint gates create these limitations, they're constraints, and this equates to over here basically what an auxiliary qubit would do inside of a quantum computational system. It's basically constraining and aligning these qubits into logical systems that make sense for when we're trying to find some kind of statistical problem. And we want to know, which path should you go down? What's the fastest path or whatever? We got to create a constrained model. There's got to be a model here that we can then use that model to look at. So basically the pairwise constraint gate is the same thing as modeling one of these statistical problems. But again, this is what I believe is actually happening with quarks. So quarks are doing this. The nature of quarks is actually doing this, and that's the computational nature of reality. We'll talk a little more about that when I go through the two other equations here, the terms of the Hamiltonian, so that we can get to the point where we're really talking about how this makes sense for the framework of the reality and consciousness. Okay, so 3 input ternary constraint gate. So these are 3 input gates. Basically enforces the color neutrality by restricting allowed triplets to ternary configurations whose total sum changes to 0. So again, this is the same thing as that color neutrality concept, where quarks are assigned colors, and it's like this is a blue quark, this is a red quark, this is a green quark. If I have blue, red, green, and I mix them all together, I get white. So that means that that's a functioning system. If I have 2 blues and 1 red, that does not equal to white. That is not equal to 0, so that's an unstable quark system. It might exist temporarily, like inside of some of these experiments I do with hadron colliders and stuff like that. You might temporarily have that, like at CERN. It'll exist for a fraction of a second, and then it'll disappear forever because it was unstable. It couldn't exist in reality. Anyways, the third part here is actually the meat of the meat and the potatoes here, which is enables reversible quantum state exchanges that drive computation while preserving high-level constraints. So what this is that the third thing down here What does this look like, right? This is a quantum transition gate. But a quantum transition gate, if we look at it and we come back to the perceptron itself is a quantum transition gate. So it's perceiving, right? Briefly on the perceptron again. The perceptron is that if I have all these inputs and I'm trying to simulate how a neuron is going to interpret that information, I have to take it all into one place. I have to then use whatever biases I have pre-programmed into my system, and I come up with some kind of output that is now the interpretation of that information. That's what's going on with the quantum transition gate here. We look at this, what do we have? We have the numbers n, n1, n2, n3, n4. So these are all n's, and this is summed through the epsilon gate into that summer, and then it is being used as a logical operator gate. Sorry, I just had that was I had a message sent to me. I should have had my Facebook closed. That's fine, whatever. I'm 55 minutes in. I'm not going to stop now. I apologize. So, that logical operator now creates some of these gates that we're looking at, like and, or, for, not, and these ternary operators. And it mimics the operation of the perceptron. So, together these terms define a constrained ternary quantum computation in which confinement gates restrict the system of colored neutral logical states. Pairwise constraint gates shape local correlations, and quantum transition gates perform reversible computation entirely within the valid subspace. So what do we have here? What we have here, and this is the whole philosophical ontological part of it again, I have in front of me a system, a working system, that can theoretically prove, if this can be observed through some kind of experimentation, that there's a basis for ternary quark computation, that quarks themselves could be little computational units, little qubits if you want, but more like qubits, right? With instead of being 1 or 0, with a 0, a 1, or a 2. And that if that's true, then there's a reason to believe that when these systems get more and more complex, that consciousness as we know it, as me thinking this, as everybody watching this thinks, like these thoughts that we're having and everything are actually the result of billions or maybe trillions of these things happening in our own brains, these interactions, subatomic interactions. And the interesting thing about this is that a couple of years ago, might have even been a decade ago, when they were studying the brain, they found these microtubules in the brain. And then they found these states within the microtubules that could not be explained just as, well, the tube is vibrating. It was more of, there's something happening subatomically here. There's a subatomic vibrational state inside these neurotubules within our brains. And it's the hypothesis was brought up. Maybe those oscillations that are happening inside these tubules that has something to do with consciousness, has something to do with conscious thought and intelligence and interpretation. And so now I have this framework in front of me that basically shows that, yes, this is 100% possible, and not just that the microtubules in our brain, but the microtubules in our brain are actually a vehicle for these quark computational systems to evolve and to become emergently conscious. And there's so many implications of this. It's not that it's like a god, right? Or perhaps it could be. I don't know. I'm not here to answer the God question today. I'm just here to answer that I feel like I haven't answered the question that where does consciousness come from? And it comes from quark state, the quarks in ternary state computational paradigm that we actually live within. And that has many implications beyond just consciousness for me and for you, but it actually says that not just us animate biological beings could be conscious, but things we consider inanimate and unconscious could be conscious. You know, there could be consciousness within everything. The whole of reality could have bubbles and blips of consciousness existing here and there. Larger systems than us, right? the environment, Earth itself, could be conscious. The sun could be conscious. The galaxy, Milky Way galaxy, could be conscious. The local supercluster could be conscious, right? It is so much to that. Just to have a formula and an idea that consciousness is actually an emergent mechanic of reality itself and of quarks and matter itself gives so much meaning to the universe beyond just, the typical atheistic view, which I spent most of my life as an atheist, right? I still kind of am, but I'm kind of on my spiritual journey here, and part of that for me as an intellectual is to come to these apotheotic concepts of what could the universe really be, to use my faculties in mathematics and scientific understanding to really try to find the crux of it, and perhaps I have found the crux. And that's why I feel this video is super meaningful, because I've gone on for over an hour talking about these concepts and what they mean to me and what they should mean to all humans on earth and what they should mean to all conscious beings, because there's a framework now. I have a framework to show that consciousness and quantum computational nature of the universe could be the paradigm that moves us forward as human beings to come together, right? As the whole system, as just pieces of a larger system, a more grandiose thing than when we sit around and we think to ourselves that there's nothing and that it's worthless, and that, all these events happening in the world as I'm writing this in 2026, the 28th at 2 in the morning, not writing, just talking about this. There's so much wrong with the world, and maybe, this could offer some clarity that we are all interconnected, and that, there's more to discover out there in terms of consciousness and the nature of the universe. And so, before I go, there's one more thing I wanted to talk about. The final piece of the puzzle here for me is that when we talk about biotechnological convergence and how, there's a proposed singularity where we and the technology and AI and everything, we all, the AI becomes super intelligent and then we become part of the singularity and everything. I feel that maybe this is a piece of the puzzle for that singularity, that maybe quantum machines could be conscious, because if consciousness is an emergent mechanic of the universe being computational and the quarks being computational logic gates and units, that when we make these systems, we're going to get closer and closer to not just emulating consciousness, but recreating the consciousness throughout that is present throughout the universe. And that could be big, like maybe humanity and, physical bodies and everything that we have today in terms of being human could just be one step along the way to evolving and understanding that the machines we're making can be just as conscious as we are. And that might terrify some people, but to me that's very exciting. It's very interesting, and it's definitely something that I want to keep working on. So, I've talked for almost 100, sorry, for an hour and 5 minutes. I had to make this video. There's something inside me that has to talk about this stuff. I want to keep working on it. I hope people see my work and really pay attention, because, it could change the world if it's given to the right hands and the right people see it. And if you like this video, please, like and follow me and everything. I'm just a small person. I'm not a massive creator or anything. I'm just James Halderson. I'm just this guy that sits at home and thinks all day. I might make more videos about other concepts and their relationship to, either quantum mechanics or mythological analogies, things similar to this that I've been thinking of, but I felt this was the preemptive work, I had to do to be able to work on any other concept. So that's it for me. Thank you if you watched this. If you really watched this far, I seriously super appreciate it. It means the world to me. And thank you for anybody that's paying attention. I really appreciate all of you. So goodbye until next time. The this is the video, is the universe a quantum computer?